Hi, welcome to today's talk on density and pressure. What are we learning? We're going to review the states of matter. We're going to define density and pressure. And our essential question will be, what are the physical properties, density and pressure, and how are these properties measured? First, let's review the states of matter. Starting off with solids. A solid keeps a definite volume and a definite shape. The atoms are held together by electric forces, and those are modeled here by little, say, springs. The idea is that these atoms, even though they are in specific places and are held together in specific places, they do vibrate. Anything that has a temperature over 0 degrees Kelvin does have kinetic energy. Liquids exist in a higher temperature than in the solid state. The molecules are not in any fixed position and are free to move around. They are loosely bound to the other molecules. Now, solids and liquids both resist compression. Now, in gases, molecules are in constant random motion and exert only a weak force on each other. The distance between molecules of a gas are really very large, especially compared to the size of each molecule. But they're mostly free and non-interacting. Now, gases are easily compressed, and we'll be getting much more into that when we talk about gases in our thermodynamics section next. Let's say you had two equal masses of, say, aluminum and gold. The first thing that you would see is that the aluminum, let's say a certain mass of aluminum, would take up over 7 times as much space as the gold. The gold is much more dense. So we're going to define density, and we'll use the Greek lowercase rho for that, as the mass divided by the unit volume. Now, our SI unit for this is going to be the kilogram, or 1,000 grams, per meter cubed. Our SI unit of length is a meter, but whenever you're thinking about volume, just imagine a cube with a length times a width times a height. So that is meters times meters times meters, or meters cubed. The densities of most liquids and solids only vary just a little bit with temperature and pressure. For gases, though, the densities vary a whole lot depending on temperature and pressure. And again, we're going to look at that when we talk about thermodynamics. Now, under normal conditions, the densities of solids and liquids are about 1,000 times greater than the densities of gases. Let's take a quick moment to review through some of the quantities that we've been talking about here, that we're throwing about. First, mass. Mass is the amount of matter or stuff that an object has. The SI unit is a kilogram, or 1,000 grams. The symbol that we'll use, we'll see that either as a lowercase or a capital N, depending if we need to differentiate some things. The measuring device that we'll use will be a balance or some type of scale, and there's not really an equation for this. Volume is the amount of space that an object occupies. It will be measured, the SI units will be meters cubed, or a meter times a meter times a meter. We'll use a capital V for that. We actually use that for a couple other things, like voltage, but we'll try to keep those from getting too mixed up. The measuring device that we'll use for that, for volume, will be mostly a graduated cylinder, even though we could use a ruler to measure length times width times height. The equation will depend on the shape of the object, but for your most basic shape, like a cube or a rectangular box, it will be length times width times height. If you kind of keep that in mind, it'll help to keep that straight. Density, and it's the amount of matter per volume. So we're going to take kilograms and divide it by cubic meters, or a kilogram per cubic meter. We'll use the lowercase Greek letter rho for that. And we will have to use like a balance and graduated cylinder for that. So that is something that we'll really be calculating. And of course, our equation is rho for density, and it's actually defined as the mass per unit volume. Again, you might see mass as a capital M. Next, we want to review what we mean by weight. Weight is the force of gravity on some matter or on a mass. It is measured in newtons. You might be used to the English system of pounds, but we'll be using newtons here. You'll see it as a symbol of the force of gravity, or F sub g. You might see it as a capital W or a lowercase w, or we might see it as mg, because looking over here, here's the equation. The force of gravity on a mass is the free fall acceleration times that mass. A spring scale, a force meter, all of those will be what we'll use to measure weight. Now let's define pressure. Pressure is the force on an object per unit area. The SI unit that we'll use for that is the Pascal. Force is measured in newtons. Area will be meters squared. Now, the force on this object here, from the fluid around it, this liquid, the force on that fluid is going to be perpendicular to that surface. Which brings us to the next point that we need to make sure that we keep straight in our minds, that the idea that while force is a vector quantity, and remember, a vector quantity is something that has a magnitude, how much, and a direction. Vectors have direction. Force is a vector quantity, but pressure is a scalar quantity. Pressure does not have a direction like force does. Now, the pressure at a specific point of a fluid can be measured with something like this. Let's say we have a cylinder and we have a vacuum in it. There's no pressure here at all. This is a piston. The piston has an area. The fluid is exerting a force on that, a force per unit area. Now, if we calibrate the spring or make, say, marks along here, we can tell how much pressure there is by how far this piston is pushed down. And of course, there's the classic bed of nails. And this is actually Professor Surway here, who wrote your textbook. And he is lying on a bed of actual nails. This is not photoshopped. Now, with many nails, you have the force of his weight over the area of each one of those. Even though they're tiny nails, there's a whole lot of them. So the area is much larger. Now, think about that compared to a single nail, stepping on a single nail, pushing up through your foot. Now, that's a very small area with that same force. Now, think about this. What if he were sitting on this? Much smaller. What would that be different? Smaller area. Or standing on one foot, or maybe even a tiptoe. Let's do a quick summary here. So here's our states of matter: solid, liquid, gas. The mass for all of these is constant, conservation of mass. The volume for both solid and liquid are constant. The density is constant on the most part. Now, the shape of a solid is constant, whereas liquid is variable. Now we go back and look at the gas. We see again that we have a constant mass. The volume will be variable. It's compressible. The density will be variable because the volume changes. And the shape, it will take the shape of the container that it's in. Density is the mass per unit volume, or kilograms per meters cubed. Pressure is a scalar quantity. It does not have direction. Force is a vector quantity. It does have direction. Remember to complete your Cornell notes, rewind and review as necessary, and thank you for listening.